Okay, so I just would like to make a brief recap of what we did last time. We are still in the topic of assessment of water resources availability, but we are now focusing on groundwater. And I made a long premise last time to highlight the importance of this problem, the importance of groundwater resources for sustainable water supply. And I highlighted the uncertainties that in practice gives the need for being supported by a modeling experiment, by a model, because relying on observations only for groundwater is particularly a challenge, because observations are provide only a little information and very often don't give an indication of the sustainability of what we are doing. So I said in this case, it is particularly important that we couple the information that we can gain from observations with the information that we can gain from a model. And then we started discussing the equations that may support a groundwater model. And we said that we need to rely on conservation equations like we do for surface water. And indeed, we started with the mass balance. Now, I'm going to share my Blackboard, which is here. And you see that there is already copied in the Blackboard the elementary volume. I copied the figure in the website, in my web lectures, but it's the same figure that we by hand depicted in the Blackboard last time. And you may remember that after some mathematical development, we got to this form of the mass balance equation for this elementary volume. And the form was that the derivative, let me see if anything is okay with my pen. Not really, 1 second. Yeah, okay. Yes, the derivative of W, and W is the volume that is stored in this elementary volume, which has coordinates X, Y, Z in space, but also W depends on time. So the derivative of W with respect to time is equal to, and after some mathematical development, we said that it's equal to the derivative of the flow in the X direction, which again depends on X, Y, Z time with respect to X with the minus sign. And then we have the analogous derivative minus derivative of Qy with respect to Y. I'm dropping the dependence of Qy on the coordinates for the sake of simplicity, and minus the derivative of Qz with respect to Z. And this is multiplied by the 3 elementary increments of the spatial coordinates. This is the equation that we wrote last time. And then we introduced the concept of volumetric specific storage. And we indicated this volumetric specific storage with the symbol SS. And we said that this is the volume of water that an aquifer releases from storage per volume of aquifer and per unit decline in hydraulic head. And then we can substitute basically, let me write the definition. SS is volume of water that is released by an aquifer per unit volume of the aquifer and unit decline of the hydraulic head, which I indicate with the symbol H, which depends, of course, on the 4 coordinates. So we said also what is head, which is basically a pressure that is given by the water column that is insisting over the aquifer. So if we apply this definition, we can say that if we apply this definition, we can say that the derivative of W with respect to time, which is the water content into the elementary volume in the aquifer, can also be written as the product of SS by the derivative of the hydraulic head with respect to time, the X, the Y, the Z. Because in the right-hand side, I just applied the definition. So what it's written here, it's the definition of volumetric specific storage. Because, I mean, given that SS is the volume of water that is released per unit volume and unit decline, of course, if I multiply SS by the change of the hydraulic head with respect to time, and I multiply SS by the volume, the X, the Y, the Z, then of course I obtain the change in the volumetric content W with respect to time. So I obtain the left-hand side. But then I can substitute in the above equation, and then I can say basically that I take the right-hand side of the equation, just one second. I take this right-hand side and I bring it here. Okay, so let me now rewrite it. I can say that minus derivative of Qx with respect to X minus derivative of Qy with respect to Y minus derivative of Qz with respect to Z. I just rewrote it. This is, and I dropped the X, the Y, the Z, but I can say that this is equivalent to the derivative of W with respect to time, and then I can substitute with this one. So I can say that this is equivalent to SS, derivative of H with respect to time. What I dropped is the product, the Y, the X, the Z here, and here again, okay? Because they are in both sides of the equation, so I can drop them. Okay, very good. And therefore, I can, in compact form, I can say that minus the divergence of Q, and then let me here highlight the dependence on the coordinates, minus the divergence of Q, where Q is a vector now, it's equal to SS derivative of H, X, Y, Z, T with respect to time. Okay, this is a simple substitution. So remember what is the divergence? The divergence of the vector Q is what you can see here. What you can see here. So if you have the 3 components of the vector Q, Qx, Qy, Qz, and you derive them, each of them with respect to the related spatial direction, then you can say that this is the divergence. And the divergence of a vector is a scalar quantity. It's a number, it's no more a vector, okay? And then we get this equation. So this is known in other field, this equation here, and let me just track it. Okay, just one second, I make 1 second. Okay. Oops, sorry. So let me just track it in another way, because this is what I was doing. It's too complicated. So this equation here, in other fields, is also known as the diffusion equation. It's a partial differential equation. It's also known in other fields as the heat equation. So it's a typical equation that we encounter in many fields of engineering. And it's, as I said, a partial differential equation. Precisely, it's a parabolic equation, but we don't want to go into the details. The thing that we can note here is that we derived this equation by imposing mass balance, which is fine, okay? We didn't impose any energy balance so far. So we can understand that there is something missing here. And indeed, if you look at this equation, we have two unknowns, and the unknowns are both Q, the flow, and the H, the piezometric head, the head of the aquifer. So we have both flow and the head, which is a synonym of energy, that are unknown. And therefore, I cannot solve this equation by itself. I need to combine this equation with something more. And in fact, this is also what I can perceive based on my intuition, because this is only a mass balance equation. There is no energy balance here. So the second equation, it's, I said, an energy balance. Actually, to be more rigorous, I should say that it's a momentum equation. And the momentum equation, conservation of momentum, reduces under certain conditions to conservation of energy. And the momentum equation is given in fluid mechanics. If you have some background of it, it's given by the Navier-Stokes equation. We don't want to go into the details, okay? I just want to mention to you, in case you have some background in fluid mechanics, that it's the Navier-Stokes equation that we have to plug in into this mass balance equation. But the Navier-Stokes equations are a bit complicated because they are very general. So let me introduce some assumptions in order to make the momentum equation simpler. And the assumption is that the flow is slow and viscous. There is no turbulence. And under this assumption, we have a well-known equation that describes conservation of momentum for fluid flow under the assumption that we have no turbulence. And this well-known equation is Darcy's law, okay? There is a lot of literature on the Darcy's law. Let me just share my screen 1 second and go to my web page, because I want to give you just a brief example. And here you see there is a link on the Darcy's law, which is, again, it's valid for laminar flow only, no turbulence. So this law basically describes the relation between the flow and the energy decline, okay? And it's valid only, this relation is valid only when the flow is laminar. And it was derived by Darcy in an experimental way. It's a physically based equation, which was derived first experimentally. And basically what Darcy did, let me see if there is another figure here. No, what he did was simply to use a pipe that you can see on the screen. And in this pipe, there is, inside the pipe, you see the dots, there is a porous media. And Darcy just let water flow through this pipe, okay? So water was entering from the left, from the small pipe on the left, and water was outflowing from the right. You see that there is the symbol Q. And basically Darcy was measured Q depending on the hydraulic head. So he studied the relationship between the decline in hydraulic head and the flow. And this relationship is precisely a conservation of energy equation, because, as I said, hydraulic head is related to energy. So if you study the flow depending on the change of energy between the two extremes of this pipe filled with the porous media, you get this relationship. And in fact, he got it experimentally. Now, Darcy's law is very simple to write, and we can write it in 3D, because so far we worked in 3D, in 3 dimensions. And now let me go back to my web page, to the Blackboard. Okay. Here we are. And let's write Darcy's law in this form. As I said, it's very simple. We work in 3D. Let me use the color black again. So we can say that Q in the direction X, which depends on the 4 coordinates, is given by minus, I tell you why minus, a constant capital K, which multiplies the change of hydraulic head with respect to X. So what happens here? You see, look at the right-hand side. In the X direction, you have a change of the hydraulic head, okay? It's a change that is multiplied by a constant capital K. And let's now just postpone a comment on this constant. So the change in hydraulic head in the right-hand side along the X direction regulates the flow in the X direction, which is placed here on the left-hand side. So you have a flow QX, which is originated by a change in hydraulic head in the same direction. Why the minus sign? Because if you want to originate a flow, you need a decline of the hydraulic head. So the flow is positive. The change derivative of H with respect to X is negative because it's a decline. And therefore, to relate a negative quantity on the right-hand side with the positive quantity on the left-hand side, you have to introduce a minus sign. Okay? And then there is K. K is a proportionality constant. It's called hydraulic conductivity. Hydraulic conductivity. Let me write it here. So K, this one, is hydraulic conductivity. Its dimensions are velocity. So, or let me say, not meters divided by second, let's stay very general, length divided by time, okay? So, hydraulic conductivity is a constant, which is then a behavior of the aquifer. And you understand its importance, it's extremely important, because it relates the change in hydraulic head, the change of energy, with the flow. And of course, the higher the K, the higher the hydraulic conductivity, the higher the flow, which means that you expect that hydraulic conductivity is larger for a very coarse aquifer, a very porous aquifer. For increasing porosity, you expect an increase of the flow for the same change in hydraulic head, and therefore you expect an increase of K. But this is in the X direction. And then I can apply the same equation in the Y direction, Qy, and let me drop the dependence on the coordinates for the sake of simplicity. This is equal to minus K again, derivative of H with respect to Y. And then I can write Qz equal to minus K, derivative of H with respect to Z. Now the question is K constant in the three directions? Well, it can be constant, it can be not. And if yes, if it is constant, if yes, we say the aquifer is isotropic. Just let me check. I'm not sure if I write correctly in English. Let me see. Okay. 1 second. Because I don't remember the spelling. So yeah, isotropic, yes. And which means that the behavior are why? I don't see why. Okay, let me just do like this. Very good. I am not sure what you see. I think you still see the graphic Blackboard full screen. If not, just let me know, please. And so isotropic means that you have the same hydraulic conductivity in the three directions of space. And let's assume that it's our aquifer is isotropic, but let's also say that it may happen that it's not. Okay. Of course, if you work in a real situation, it's likely that it's not isotropic, but let's assume for now, for simplicity, that it is. And also let's note that in principle, K, if the aquifer is not homogeneous, it may vary depending on the coordinates, X, Y, Z, if the aquifer is not homogeneous. If it is homogeneous, it doesn't depend on the coordinates. So for now, let's suppose that K is constant, is a full constant in the space and along the three directions. Okay, very good. Now, of course, what we see is that the Darcy equation can be substituted into the diffusion equation, okay? And in particular, you see that if you look at the diffusion equation in the form that I am now highlighting with the brown color, this one here. Okay, so if I look at the formula here, you see that in the left-hand side, what I have is the three derivatives of Q with respect to the three directions. And therefore, I can substitute these three, Qx, Qy, Qz, into here. Okay? Into here. And if I make this substitution, I am coupling the two equations. And basically what I'm doing by coupling the two equations is to eliminate Q from the equation. Because you see that the Darcy equation gives Q depending on h. Let's suppose that we know k, okay? K is known. The Darcy equation gives q depending on h. And therefore, if I substitute in the diffusion equation, I get the result of eliminating q. Now, let me take some room here to make this substitution. And let me just 1 second, I need to expand this blackboard. Let me make it larger. Very good. Okay, and then let me expand the layer. Good, and now let me put, okay, perfect. We are already here. Okay. Now let me make this substitution then. So this is the equation that I have to grab. And so let me write it in this way. Let me write with the red color to make a difference. Now let me write it in this way. Let me just see if I can. One second. I wanna make it a little bit smaller. Okay, very good. So you can see on the screen everything. Perfect. Now, let me write it in this way. Derivative with respect to x, and I'm referring to the derivative of qx. So I substitute it as a derivative with respect to x of k, derivative of h with respect to x, plus. So let me see what I wrote here. And what I wrote here, I wanted to write the derivative of qx with respect to x, okay? And which is the element that you see here. And I wanted to substitute with, and it has a negative sign, I wanted to substitute with this element here. And therefore, the two negative signs compensate, and I can write that it is equivalent to the derivative with respect to x of k, derivative of h with respect to x. And then I can write the derivative with respect to y of k, derivative of h with respect to y, plus the derivative with respect to z, k, derivative of h with respect to z, okay? And this is the left-hand side of the equation, and then it's equivalent to ss, derivative of h with respect to t. This is the resulting equation, and you see that q disappeared, okay? And now what I can write, I can take k as a common factor, so k which multiplies the second derivative with respect to x square of h, plus the second derivative with respect to y of h, plus the second derivative again of h with respect to z square. And this is equivalent to ss, derivative of h with respect to time. Okay, so at the end of the story, I can write it in compact form as the product of k by nabla square, which is the Laplacian operator of h. Let me now write the dependence on the coordinates, which is equal to ss, derivative of h, again depending on the coordinate, z t, with respect to time. Oops, sorry, with respect to time. Okay, now let's look at this equation that I got here. Because this is what I wanted to achieve. It's an equation that has only one unknown, which is h, and it's then solvable. It's a combination of a mass balance equation with the Darcy's law, which is an energy balance equation in the three directions of space. And it's solvable. Of course, it's you know, it's a second order equation, so it's not easy to solve. And but it is a tool that I now can use to describe what? To describe the dynamics of the hydraulic head in the three directions of space and time. And once I know the dynamics of the hydraulic head, I can go back to these equations here, bottom left. And once that I know H, hydraulic head, with the Darcy's law, I can describe the flow in the three directions of space. So what I got at the end, a description of how water moves in the underground, which is, from a technical point of view, it's, you know, it's extremely useful. Because if I can describe how water moves in the underground, I can describe what happens when I take water from a well. I can describe the replenishment of the aquifer. I can describe the velocity of water into the aquifer, because describing the flow means also describing the velocity. And I can describe the recharge time. The recharge time is what matters for sustainability. So it is a very annoying mathematical development, very boring, not easy to follow, which at the end of the story gives an extremely useful tool for technical design. Provided, of course, we can solve it, because the equation is a differential equation. And the differential equation doesn't give you the value of the variable. It gives to you the change of the variable, not the value. So here we are describing the hydraulic head H, but we are describing, as you look at the equation, we are describing the second derivative. So we are describing the change. In order to describe the original variable H, we need to integrate it. So provided we can solve it, this is extremely useful. And in order to solve it, we not only have to deal with a mathematical burden, we also have to deal with the gathering, the collection of the required information. And what is the required information? The required information is, first of all, the description of the parameters of this equation. The parameters are hydraulic conductivity and volumetric specific storage. We already said that these are very important. We need to describe them. We can make assumptions like they are constant, like I did here in this equation. I assumed K and SS are constant. So I can make assumptions, but still I need these parameters. And these parameters depend on the porosity, I already told you, depend on the behavior of the aquifer. So I need to know these behaviors. And also I need to know the geometry of the aquifer, because of course the geometry it determines the solution, because the integration of this equation is to be performed over a spatial domain, and the spatial domain is given by the geometry of the aquifer. I need to know the thickness, I need to know the areal extension, several things I need to know. And keep in mind, as you know, that any differential equation needs, in order to be solved, the initial and boundary conditions. Okay, I assume that you already know what are initial and boundary conditions. And if you already know what they are, you know, it's you know that it's not easy to get them. Okay, because you see, this equation describes the changes in space and time of H, and if only the changes are described, I need to know what happens at the boundaries of these changes in order to get a full description of the hydraulic head in its complexity. Now, how it's called, this equation? It's called, again, this is a Laplace equation, and or let's say it can be reduced to a Laplace equation in steady state conditions. If you take the derivative with respect to time equal to 0, then you get this, the right hand side that goes to 0, and the left hand side describes Laplace equation. So let me write in the top of the blackboard. If I take if the derivative of H with respect to time is 0, then the equation reduces to K. Can you please,
I don't know this time again, no, because this
sorry?
time is supposed to be 8.
Can you repeat the question, please?
No, I opened the page because you know that the internet takes time for it to open. I opened the page so that
I don't understand the question. I'm sorry. Just 1 second, because I guess that you cannot see the blackboard. I don't understand. I don't understand if it was a question or not. Let me just move forward then. And I'm writing on the top left, top right of the blackboard. So if the derivative of H with respect to time is 0, the equations reduces to K nabla square H equal to 0. And this is the Laplace equation. It's also called Laplace equation. If you don't know what is the Laplace equation, don't worry, it's not relevant. And what I was saying is that resolving this equation is a complex problem, but we can take simplifying assumptions, like the steady state assumption, like in this case, which means that it reduces to a form that is much easier to handle. And another simplification that we may take is that we can consider the flow only in 2 directions. So we can eliminate the derivatives with respect to the 3rd direction, and then we get a 2D, 2-dimensional problem. Or we can consider that the flow occurs mainly in only 1 direction, therefore reducing to a 1D problem. Now, we don't want to go into the details, and it is just enough that we know that through this equation, we can solve our problem by referring to a 1D solution, a 2D solution, or a 3D one in steady state or unsteady state. unsteady state. Very good. We don't go into the details, okay? Because, as I said, it's a complex problem, but there is one thing that I want to tell you, because you may think that this is something that goes beyond our capacity, which is not the case, because actually, let me now go back to the web and share the blackboard. Then, actually, we have models for, sorry, I made a mistake. We have models for solving this equation, and we can use these models. And let me give you an example. Just 1 second. I wanna. Okay, because I wanted to maximize the view on my phone. Otherwise, I cannot check what you see. So let me open another web page and let me look on the web for groundwater model or groundwater modeling software here. And you see that there is a lot of entries for groundwater models. What are these models? These are models like iMod, for instance, that are already prepared and help us to solve the problem. And there is a particular model that I want to show you, which is widely used all over the world for precisely for studying the sustainability of water withdrawal from aquifers. And this model is ModFlow. I just clicked on the link. This is a model that is freely available. It's produced by the United States Geological Survey, and it's indeed a model that requires a lot of information, but has the nice feature of performing the integration of the groundwater flow equation for us. And the model can be downloaded here. And let me see, where is the download page? Here. Just 1 second. And here is an overview of the model. And there is also the download link. It's a model that it's not easy to use. And I did a couple of master degree theses on the use of this model, application to specific problems. And it's, you know, it's a bit complicated because it's a numerical model. So the solution of the equation is not analytical, it's numerical, and therefore there is approximation in it. And you have to be careful when using numerical models, because you have to be able to assess the amount of approximation, and you have to be able to assess the reliability of the results. Keep in mind that as an engineer, when you use a software, you are not excused if you produce a wrong result. You cannot say that it's not your fault, but it was a problem of the software. When you put your signature under a design project, you take the responsibility for it, no matter if the mistake comes from you or from a software. You are responsible for what you sign, and if the error comes from a software, the assumption, for instance, of the judge that has to evaluate your responsibility, the assumption is that you have to be able to assess the reliability of what a software produces. So this requirement of being able to assess if the output from a software is correct or not, this requirement is the reason why you have to know the theory. So why did we spend 2 hours to study the groundwater flow equation? Why did we get into that burden, into that mathematically annoying development, if we have a software that can make the computation for us? The answer is because if you know the theory, then you can elaborate an expectation of how the result should look. And if you are capable of elaborating an expectation, then you have the capability to understand whether the output from the software is correct or not. So the moral of the story is you have to know the theory, because the theory allows you to elaborate an expectation. You may not realize this, because at the present stage, you may say, well, I know the theory, I assisted to the development of the groundwater flow equation, but still I cannot elaborate an expectation. This is correct, because you still have to study it. I tell you, and I am dead sure that if you understand the theory, understanding means that you digest it, you understand it, you have a perception of it works. I assure to you that if you understand the theory now, then you become able to elaborate an expectation of how the results should look at. There is one nice thing of related to the use of the software. Usually when a software makes a mistake, it's not a minor mistake, it's a big one. Because the software may give you, for instance, a negative value for the hydraulic head. So in this case, it's very easy for you to understand that something is wrong. So there is this nice feature of the software. You don't have to be able to assess tiny errors. It's just sufficient, it's just enough that you become able to recognize big mistakes. And the knowledge of the theory helps you in that. 1 second, because I have some colleagues of yours that are in the waiting room. 1 second. Okay. So this is the reason why we study the theory. And this is the reason why it's important that you understand the theory. Okay, so I think with the groundwater flow, we can say that we are happy. There is not much more that I can say. And you have several links in the web page if you want to expand your knowledge. I just wonder, before I pass to the next topic, if you have any question for me. No questions. Yes. Okay, that's fine. Very good. So, just a recommendation before we move forward. Don't be discouraged by mathematical developments, and don't get annoyed. If you get discouraged or annoyed, try to find the link between the equations and what you see in the field. Because I tell you, there is a direct relationship. I'm sorry that this year we cannot make any field trip, but it is extremely important that maybe by using the web that you try to get a connection of between what you study and what you see on the field. And I'll give you an example later on how you can find on the web something that helps you to identify this connection, even if we don't have the opportunity to make a field trip. Okay, good. Now, let me move to the next one then. And just 1 second, I close the page of ModFlow and I can go back here. Okay, so this is the page of our course, and we got here deductive methods. We finished it. Okay, We already did, by the way, model calibration and validation. And therefore, this is something that, of course, we don't have to repeat. Now, the next one is design of river barrages. And let me just show you the calendar, by the way. We are here, April 12. And I just want to remind you that we meet next Thursday, and then we have 1 week break, okay? And we meet again April 26, because I have, as I told you, I have to attend a virtual international conference, so there is a break between these two dates that you see on the screen. So next Thursday we meet, and then we have 1 week break, okay? Good. Now let me go to design of river barrages. This is something that it's more interesting, more funny, let's say. It's very, very technical in terms of design. And just 1 second, I look at the end of the lecture. Yeah, okay. And so what are we talking about? We are talking about something like this picture here, okay? What is this one? It's a river barrage. There is the river flowing from upstream. Upstream is behind the barrage and flowing downstream. And you see that in order to flow downstream, the river has to surmount to pass over the barrage. And what is the purpose of this construction? In this case, there are several purposes for which you may decide, an engineer may decide to build a barrage. In this case, the purpose is to fix the water level upstream, to keep upstream a high water level. This is the purpose of this barrage. And why do we have this need? For instance, because upstream, we have to get water from the river. And if you want to get water from the river, you need a high water level, because water flows down by gravity. And you have to get where you get the water, you have to get a fairly stable water level. You don't want the water level of the river to change a lot from one season to another one, because if you put there a pump, if you put there a pipe to get the water, you need some stability. You cannot move the pump and move the pipe every day. You need some stability. So this is the reason why we build these barrages, in order to, as I said, to stabilize the water level upstream. And you see that in this case, you have a bridge over the barrage, which may be conceived for just surveilling the barrage, or maybe a bridge where the car or the bicycle pass. This is an example of river barrage. Let me now open a Google page and let's see other pictures. So I'm just looking by chance, okay? River barrage. And let me look at the images. So there is the one that it's related to my page. This is good, that the first entry is my web page. And this is, let me see some meaningful pictures. This is a big barrage. You see the difference between the water level upstream and downstream. Upstream, you have a kind of a lake, so a more stable level. Downstream, you have more variability. Okay, this is a rendering, it's not a picture. And here you have another example. Here upstream is on the part of the picture that is directed towards me, I think, because I see more water, I'm not really sure. And here you have a barrage that looks like a dam more than a barrage. We will see the difference between dam and barrages. There is a clearly defined difference. Now let me look at this one, because this refers to a Wikipedia page. Okay, and you see that the Wikipedia page, just 1 second, it puts between parentheses dam. Actually, we will see there is a a huge difference between a barrage and a dam, and we will clarify it, okay? And this is something that I think it's a barrage, not a dam, but I anticipate that the difference is just the height of the construction. And the height of a barrage should not pass, according to the Italian regulation, 15 meters. We will see the details, okay? And so I think this is less than 15 meters, so this is a barrage, in my opinion. And you see that this barrage is equipped also with gates. You see that there are some stuff here. I cannot, let me just see if I can increase, if I can zoom. You see this mechanism here. Look at my mouse where it's going up and down. This mechanism allow one to lower the threshold or the weir, because in the threshold of a barrage, which means the upper part that has to be surmounted by water, is called weir in technical term, W-E-I-R. We will see with more details. So I can, through these mechanisms, I can lower or increase the level of the weir, the level of the threshold, which means that I can regulate the water level upstream, okay? And in fact, you see here in the extreme left, look at my mouse, the weir is closed. There is no water flowing down, okay? Okay, and let me see if there are other pictures. Okay, this is a big barrage. Not sure whether it's a barrage or a dam, but I think it's a barrage. This is another example with a bridge on the top of it. And let me browse back the figures. And here you see in this barrage, if you see on the right, you see that there are gates. So also in this case, you can regulate the water level upstream. Okay, let's, I think that's it. And you see in Wikipedia, we have also weir. And the weir, it's what the term I introduced before. And you see some examples here. Okay, now let's see this figure. I think it's interesting. This is a very small barrage, okay, with a bridge over it. It's made by mixed wood and concrete. I told you at the beginning there are several purposes for which you may build barrages, and I don't think in this case the purpose was to take water. It was probably another purpose, and the other purpose may be to stabilize the level of the riverbed. Okay, you don't only stabilize the water level with a barrage, you can also stabilize the level of the riverbed. Okay, I think it's enough. Let's now go to more technical details. So let's refer to the Italian regulation to define what a barrage is. I need to refer to a regulation because when I work in engineering and I look for definitions, I look for technical guidelines, the first thing that I have to look for are the regulations. Because in engineering, I have constraints given by the law in force through regulations. So if I look in engineering for a definition, the first question is there a regulation that gives the definition? Because if there is, I need to refer to the regulation. Of course, the regulation is country-based. So in this case, I'm talking about something that is potentially dangerous. It's a dam, it's a barrage, something that in case of a collapse may originate a relevant risk. So my guess is that whatever I work, there is a regulation to dictate the procedure, the design procedures. And therefore, if I suspect that there is a regulation, I need to get it and refer to it. So in defining what is a barrage, I refer to the Italian regulation because I need to make a reference to one example. And of course, I know the regulation in Italy. But whatever you work, sometimes I also worked abroad, you need to refer to the local regulations. And remember, finding regulations, it's one of the challenges of our work. And it's not easy. So sometimes we need some help, especially when we want to find regulations about water, because it's extremely complicated, especially in Europe. In Europe, it's extremely complicated. The water governance is very complicated. Why? Because it has a long history. So in Italy, water governance has a history of a couple of thousand years. And therefore, there are some institutions that are surviving from very ancient times, which have their own regulation. So in Italy, we know that water governance is extremely complicated. And finding the regulations is a challenge. Sometimes we go to a layer, we ask assistance to a layer because we recognize that it's, you know, the issue is tough. Okay, and now let's refer to the Italian regulation here, Italian regulation. And the Italian regulation classifies retention structures over rivers. And the categories are those that you can see here. Concrete or stone masonry dams, earth dams, other type of dams, river barrages. So what is a river barrage? Already here we see that there is a difference between a dam and a river barrage. Okay, what is a river barrage? And here is the definition in Italy. A river barrage is a low head diversion dam. Low head, okay? That is built to allow a diversion of a part of the water flow. So we call barrages in Italy they are called traverse. When we say una traversa, we mean that it's a diversion facility. So the purpose is to divert part of the flow. Okay. The barrage determines a little increase of the upstream water profile and a little upstream reservoir. And you may say, how much little? I'll give you the details. Here there is written something that we already know. The purpose of the barrage is essentially to stabilize the upstream water level and the river profile. Okay, very good. And here another important thing. We can often see, especially in Italy, in mountain rivers, small barrages that are not funnelized to water withdrawal, but just to bed profile stabilizations. These structures are called check dams, while the term barrage usually identifies structure finalized to water diversion. So I just want to stress, to emphasize what I previously said. Okay. So let's look at the definition, the difference in quantitative terms between barrages and dams. In Italy, dams are defined as structures that are either more than 15 meters high, where the height is measured from the lowermost above ground to the uppermost part of the structure. Okay, lowermost above ground and uppermost part of the structure. I'll give you a sketch. Second condition, because I said either, okay, either more than 15 meters high, or second condition, originating in upstream storage of more than 1 million cubic meters, where storage is measured at the highest regulation level. Okay, now just 1 second to clarify. And let me go to the Blackboard to make a clarification. Of course, I need a new sheet. Just 1 second. Okay, this is not a nice color. Now it's better. Now, barrage. First of all, we have a river, okay? And let's suppose that this is a, sorry, I forgot to change the tool. Let's suppose that this is a cross-section of a river. This is water in the river. Very good. And let's suppose that we build a barrage here. And this is the foundation of the barrage. This is the underground part of it. Okay. So and this is the uppermost part that is surmounted by water. So what is the configuration after I build the barrage? The configuration is something like this. The water level goes up here, and then something like this, okay? And here usually I have turbulence. Okay, now this is the new configuration after the barrage. What is the height here? The height is this one. This is my height. This is the height measured from the uppermost, sorry, from the lowermost above ground point, which is this one, to the uppermost part of the structure that is surmounted by water. Okay, this is the height. And what is the storage? The storage is measured, it is this one, let me call it W. It is this one, W, and it's measured at the highest regulation level. So if this is the max level in the reservoir, max level, then with reference to this max level, I have to measure the storage. So either H greater than 15 or W greater than 1 million, dam, okay, 15 meters, W cubic meters. Okay, this is to clarify the situation. Why it's important to make a difference? Because if your structure is a dam, the technical constraints, the regulation constraints are much challenging with respect to a barrage. Okay, the dams are controlled in Italy by a national authority. And in particular, the national authority takes care of monitoring the dam structure, of making periodic checks, etc. If a barrage is typically controlled by regional authorities with much less requirements. Okay. Okay, so barrages can be classified into two categories, and we already mentioned it. Regulated barrages, which are equipped with mechanisms, machineries like gates, or regulated sluiceways. What is a sluiceway? It's an aperture through which water flows through the barrage. Okay, we also call it sluiceway. Usually, there is a difference between the weir and the sluiceway, meaning that the sluiceway usually it's a window in the structure, which is with the top part of the window that is submerged by water. Okay, the weir is a kind of threshold. It's not a window. Let me see if I can find some images for sluiceways. And let me see if there is an image that is clear. I think that the best image is this sketch here. This is a sluiceway. You see, it's a window or a hole, and it is fully submerged. And in terms of a picture, I have seen a picture here. Here you see water flowing through sluiceways. They are entirely submerged. Okay. Or you can also call it bottom discharge, but the technical term is sluiceways. And then there is the weir. The weir is, for instance, this one. It's here on the left of the picture, you see a weir. Okay. So regulated barrages are equipped with machineries that allow you to regulate the upstream water level. Unregulated barrages are structures that don't allow the regulation of the upstream water level. And then there is a third category, temporary barrages. We don't discuss these. These are structures that are usually built over summer and removed during winter. Why these are temporary structures? Because typically people are concerned that if you leave the barrage there, if a flood comes, the barrage may be wiped out by the flood, and also the barrage may induce an increase of the flood risk, because of course the barrage is an obstacle to the river flow. So in some cases people decide just to put the barrages only during the dry season. What is the difference between regulated barrages and unregulated barrages in terms of maintenance and in terms of management? Of course, a regulated barrage is more difficult to maintain, and therefore it's a solution that is more expensive. It's more demanding in terms of resources, but of course it gives the advantage that you can regulate with more efficiency the upstream water level. Here you see in my web page a map of a barrage on the river Danube, which you can zoom out. And this barrage is located at the boundary, I think, between, I would say it's Austria and Bulgaria, but I'm not really sure. Let's see if I expand it a lot. And yeah, I think maybe the boundary between Austria, yes, correct, and probably Slovakia. Let me see. No, actually, I don't think the boundary of what? Just 1 second. I don't think, maybe it's in fully Austrian. I think it's located. It's not at the boundary. It's located in Austria. And it is an important barrage. It's on the Danube. And the purpose in this case of the barrage is not water withdrawal, but it's to facilitate navigation. And this is a complex structure. And of course, it's regulated because on a so important river, you need to regulate it. And here it's nice because you can zoom it out and you see that there are the navigation docks that allow the ships to go up and down the river. And the nice thing, you see the weirs here in the center. They are weirs, not sluiceways. And in both sides there is a power plant, and a power plant which allows to produce electricity by using the difference in elevation between upstream and downstream water. There is a jump, and there is a difference in the head, and therefore this difference in the head, difference in energy, can be used to produce hydropower. And it's nice because you can zoom out, it's high definition, and you can look at the details of, for instance, the navigation docks. There are the details here. I think one interesting thing of the navigation docks, and these are the navigation docks. If you look at the extreme, at the downstream extreme, you see the gates of the navigation docks. And these are called Porte Vinciane because it is said, but it's not proved, that they were first designed by Leonardo da Vinci. So they are called Vincian gates, and in Italian Porte Vinciane. Okay, you can play with this figure to see an example. And another example of, this is an example of a regulated barrage. Now, another example of an unregulated barrage is given by, I browsed down my web page. I think there are pictures. No, they are not here. So let me just show you. Let me just show you another picture of an unregulated barrage. Give me 1 second. I need to go to the tutorials of the other course, which is in Italian, but I have the same lecture, and I think here I have some pictures. I am quite sure, which means that I have to update also your page with the same pictures. Yes, and I wanted to show you this picture. It's an unregulated barrage on a mountain river. So you see the barrage in the left part of the picture, and you see that there is a weir in the upper part, and also there is a sluiceway. And in this case, the sluiceway is used for cleaning the upstream reservoir. And you see that water is diverted, and water is diverted through a grid that is placed here. Look at my mouse, which is pointing to a grid. And you see that the water goes into the grid and comes out into this pool, in this tank, upstream tank, from which there is another grid that the water flows through, and the water is brought downstream. This is a barrage for water diversion. So precisely the purpose that we want to study together. And you see that there is a gate here, look at my mouse, in order to close the diversion. And why do we need to close the diversion? For instance, for cleaning the tank, or we need sometimes to close the diversion when there is a lot of turbidity in the river. During floods, usually water diversions are closed. Okay, this is another example of a river barrage. Okay. And now, let's focus on the unregulated barrages. Why? Because they are simpler, and for this reason, it may happen to you that somebody asks you to design an unregulated barrage. Usually for regulated barrages, the design is left to big engineering companies. But for unregulated barrages, it's a typical professional work that may happen at the beginning of the career. And keep in mind that besides water diversion, unregulated barrages are also used for producing hydropower, and in particular for serving run-of-the-river hydropower plants. We already talked about what is the meaning of run-of-the-river. It's an hydropower plant that just uses the water that is flowing in the river without accumulation. And sometimes the barrages are conceived for multiple purposes, like, for instance, both hydropower production and water diversion. Now, the first problem that one needs to solve when projecting, when designing river barrage is the estimation of the design flow. And we already know how to do this because it's related to the study of the flow duration curve. And we know how to operate when we have data available and how to operate when we don't have data. And so here there is a very short paragraph to mention that we have to refer to the flow duration curve for estimating this design flow. And the treatment is very short because we already discussed this topic. Okay. Now, I'm not sure whether we discussed also but I think yes, the water withdrawal index and the water use index. They are very simple. And the water withdrawal index is given by the ratio between the design flow and the average flow in the river. And the water use index is given by the ratio of the average design flow, of the average diverted flow at the numerator and the average river flow in undisturbed situation at the denominator. Okay, good. And this is something that we already discussed. Just keep in mind that these are typical questions at the exam, okay? Now, let's discuss about the structure of unregulated river barrages. And let me first give you an overview of the overall structure. And then we will discuss in detail the design of single parts of it. Okay. Now, let me refer to this sketch to explain what is, to discuss the overall structure of a river barrage. First of all, this is just an example. There are several structures that can be used. This is a structure that is frequently used in mountain rivers because it is the structure is elongated in the longitudinal direction. So you see that this structure doesn't occupy much room in the transversal direction. Here the structure is articulated along the river. And it's a solution that is frequently used when you have steep hill slopes in order to minimize the disturbance, the impact on the hill slope themselves. Because if you want to occupy room in the transversal direction across the river, I mean the direction across the river. If you want to occupy a room in that direction and the slopes of the river are very steep, then you need to dig a lot, to excavate a lot. And when you excavate at the foot of a steep slope, you know, there might be stability problems. So when the slopes are very steep, it's advisable that the structure is not much developed in the across river direction. It is advisable that the structure is developed in the along river direction or longitudinal direction. I think that it's time to make a break before we discuss the single parts of this structure. I wonder whether you have any question before we make a 15 minutes break. No questions? Okay, now let's meet again at 11 o'clock. Thank you. So students, do you have any question? I think it may be appropriate that I give an award to the students that ask questions, because you know, you are not reactive enough. I already told you. Are you sure that you don't have any question now? Okay, so let me go back to this scheme. So as I said, it's something that it's just an example. I think it may be useful if I do one thing. Let me copy this image and put it on the blackboard so I can take notes over it. Just 1 second. Okay, here we are. Now let me share the blackboard and not the web page. So here. Okay, let me just expand it a little bit. Okay, I think very good. Okay, let me take this dimension here, or maybe that I can make it like just 1 second. 90% maybe. Let me see. Oops, 110. I wanted to make it. Okay, let's try 120. Good. Now it's the correct size. Okay, so let me comment on this sketch. First, water flows from the left to the right. See the blue arrow that I just drew here. And the barrage is the structure that you see here. And this is the threshold of the barrage, which is built over the side walls, and the side walls are these ones. Let me just make one thing. I want to identify the part of the structure with a different color with respect to flow. So this is the barrage. And these are the side walls. The side walls are usually built if one needs to stabilize the slopes, and they are not strictly needed. You can find barrages that are directly put into the hill slopes without the need for side walls. But again, if you want to stabilize it, it may be useful. And also this one here is the other side wall, okay? Very good. Now, the side walls may be that they have lateral bindings into the hill slope, and these are shown here. Okay, these lateral bindings may be needed if you want to stabilize the side walls to make sure that they don't collapse. And sometimes, especially when the steeps are made by loose soil, they may be an important part of the design. And of course, this part of the design may be carried out with the help of a geologist in order to understand what it's really needed to make the structure stable. Now, what happens to, let's look now at the main, at the barrage. The barrage is divided into, in the across river direction into several parts. And it's not a unique weir. There is a part that is placed at a lower level, and the part that is placed at the lower level is what is called, oops, sorry, I want to change the color. What is called the environmental flow spillway. So when you have just a few amount of water, when you have a very low water flow, what happens to the water flow is that it goes towards the part of the barrage that is placed at the lower elevation. And so when you have just a few, a very small flow, of course, water goes through the barrage by passing from through the part that is placed at a lower elevation. And this is the environmental flow spillway. So there is in the barrage a part of it that is lowered down. So if I get a view of the barrage from downstream, so if I go downstream and I look at the barrage with my eyes in this direction, okay, I get a look from the barrage from downstream in this direction. What I see is the sidewall. Okay, let me print it in red, sorry. Because I said that the flow is in blue and the structure is in red. So there is the sidewall. And then there is a connection between the sidewall and what is called the main spillway. Okay, and this is called, this connection is called wing. And then there is another wing here. And then there is the environmental flow spillway. Let me just make it with the lower size. And then there is the other sidewall. Okay, so this is again the wing. And this is the environmental flow spillway. And this is the main spillway. So you see that there is a spillway that is located at a lower elevation. And of course, when you have only a reduced amount of flow, the first thing that may happen is that you get the flow through this environmental flow spillway. And there is no flow from the main spillway, okay? Okay, very good. And what is the reason why we concentrate the flow in a spillway with low elevation? The reason is that this is the environmental flow. The environmental flow is to be released by law, okay? So it's something that is compulsory. So you must make sure that in your structure, there is a spillway that has the priority over all the other spillways. And this is the environmental flow spillway. It has also the priority over water diversion. Before diverting water, you have to release some flow from the environmental flow spillway. Some flow. How much? It is dictated by local regulations. So in Italy, we know where to refer if we want to know what is the environmental flow value for a river. It's the regional authority in Italy. But in any country in Europe, of the European community, we know that in any country there must be regulations for the computation of the environmental flow. In other countries outside Europe, probably it's the same, but of course you have to get information, okay? So this is an essential information that you need to know. The environmental flow, let's call it with this symbol, QDMV. Why DMV? Because in Italy, it was called in the past the flusso minimo vitale. So in Italy, we are used to call it QDMV. Now it's not anymore called, even in Italy, the flusso minimo vitale, because the flusso minimo vitale means minimum vital flow, which is not a good thing. I mean, it's a very bad term. Now we call it ecologic flow in Italy, but let me use this symbol anyway, okay? It's just a matter of convention. We decide to use this symbol. Very good. Now, this is, again, an essential information. You have to estimate it. And this goes through the environmental flow spillway with priority. Why do we concentrate it in the spillway? You could say, why don't you let it go through the main spillway? Because when there is a very small amount of flow, we want to concentrate it in a small space because we want to give some water depth for the fishes to survive. And therefore, in the environmental flow spillway, very often we try to create the conditions so that the fishes can climb up the barrage. So this means that it's not depicted here. This means that here downstream, you may have downstream the environmental flow spillway, you may have a fish ramp. It's not depicted here for the sake of clarity. And to make a fish ramp working, to give to the fishes the possibility to climb up the barrage, you need to concentrate the flow. You need some water depth, okay? Very good. So we concentrate it here. Perfect. Now, let's look at the main spillway. The main spillway is elevated. And what is the purpose of the main spillway? The purpose is to allow the peak flow to go through the barrage. So the main spillway is used only by the high flows. And in this case, you want it very large because you don't want to constrain the high flow in a small weir, because if you constrain it, it means that you are causing a significant water elevation upstream. And we don't want that. During floods, we don't want that the barrage originates a significant increase of elevation upstream. Okay, so the environmental flow spillway, the main spillway is large. Okay, and then there are the wings. Why we want to put wings there, and why we don't go straight against the side walls? Because we want as much as possible to keep the flood flow far from the hill slopes. So we want to create an obstacle to reaching the hill slope, and then we put the wings. Okay, and of course you may say, okay, but the wing is also increasing the water flow upstream. That's true, but you know, if the flood is very large, the effect of the wings in terms of additional elevation upstream is not very significant. And if the flood is not very large, the wings are effective in keeping the flow far from the main flow, let's say the main velocity, far from the hill slopes. We don't want water flowing with very high velocity against the sidewalls, against the hill slopes, okay? So we usually create the wings. Of course, not always. You can also see some barrages where the main spillway goes straight against the sidewalls. And it may be that in that case, the designer, the engineer, was not concerned by the erosion of the slopes, okay? Very good. Now, downstream the main spillway, you see that there are boulders, okay? Here, I am drawing in red them. There are these boulders. They are a protection from erosion because downstream you have turbulence. you have water flowing down, jumping down with turbulence. So you have to protect the place where water lands. You have to protect it from erosion. Okay, so usually we put big boulders. There are other ways to protect barrages downstream. We now just focus on this solution, okay? And we will discuss later other possible solutions. Now, let's look now at what happens with regard to water diversion. And let me just make a change in my drawing here. I wanna lower down the level of the flow in the environmental flow spillway. So just 1 second, and let me do like this. Let me make an experiment to fill it, yeah, with white color, and then let me redraw, okay, this part, and then let me, what I did was to delete and the previous water level in the environmental flow spillway and to lower it down. Now, what happens to the water that is diverted? Let's look at the view from the top. You see that there are diversion spillways here. These are the spillways through which the diverted water passes. So there is some water that goes through these spillways and goes into what is called here gravel trap. Let's discuss it later. Now I want to discuss just these two spillways. And you see that there are gates to protect these spillways. And the gates are now here. I am drawing them in a red color. We put gates to be able to interrupt the water diversion if needed. And I already explained to you what are the reasons why I may need to interrupt the water diversion. And these gates can be manually controlled or can be remotely controlled through motors. Okay, that's fine. Now, next question. What is the level of these spillways? Elevation. Okay, diversion spillways. What is the elevation? What I said before is that the environmental flow spillway has the priority. Having the priority means that it's the lowest spillway in elevation in my structure. And then I said that the main spillway is for flood flows. So it's the spillway with the highest elevation in my structure. The diversion spillway has an elevation that is in between the elevation of the environmental flow spillway and the elevation of the main spillway. So let me look at the view from downstream here. What is the elevation of the diversion spillway? It's something like here. Okay. This spillway, so this is the diversion spillway. Why the diversion spillway is placed at a higher elevation with respect to the environmental flow spillway? Because I cannot divert any water unless I release downstream the environmental flow spillway. And therefore the diversion spillway has to get a lower priority with respect to the environmental flow spillway. Lower priority means higher elevation because water goes downstream by first passing through the lowest elevation. So again, diversion spillway higher than the environmental flow spillway. Very good. And now, why is the main spillway placed at a higher elevation with respect to the diversion spillway? Because of course, I don't want any water to flow downstream unless I first release the environmental flow, second, taken the diverted flow. So I don't want anything flowing through the main spillway unless, again, I have satisfied two conditions. The environmental flow is released through the environmental flow spillway, and the diverted flow is released through the diversion spillway. And therefore, it follows that the main spillway is at the higher elevation. Okay. Now let me make a second drawing in my blackboard and give a sketch, depict a sketch, which is a zoom. Okay. So here I have the environmental flow spillway. Here I have the diversion spillway. Okay, and here I have the main spillway. I already explained why they are placed at this different elevation. And let me just write here higher priority. Okay, good. Here, middle priority. And here, lower priority. Again, when I talk about water flow, priorities in this case are given through elevation. Okay, perfect. Now, of course, I have some difference in elevation. Let me call, just 1 second, because I want to use the same symbols. So I want to make sure that, okay, let me call this difference in elevation here. Let me call it delta H1. And now I have a second difference in elevation here. Let me call it delta H2. Okay. Now the question is, what are the values of delta H1? What is the value of delta H2? Okay. Now keep in mind that you need to know, as preliminary information, QDMV, and also you need to know QP, which is the design diverted flow. Okay. Now, let's focus on delta H2, and let me find an expression for it. And keep in mind, what is the condition that I have to ensure? I have to ensure that delta H2 is enough to allow Q dmV to flow down before any water is diverted. What does this mean? What it means, what I'm writing here? It means that, as I have written, I cannot divert any water before I have the environmental flow spillway, releasing down the environmental flow. And what happens when you have a flow through a spillway? Okay, you have a flow through a spillway, and for increasing flow, you have increasing water level. Okay, so here you have water, and depending on the water level that you have on the spillway, you have a flow. And if you increase the water level in the spillway, you increase the flow, of course. Okay, and so you have to make sure that when the water level in the spillway goes up and reaches the level of the diversion spillway, what happens? You have activation of the diversion spillway. But this activation cannot happen until you are releasing a flow that is equal to the environmental flow. So basically, this delta H2 is to be determined in a way that when the water level reaches the value of delta H2, then you have to impose that you have the environmental flow spillway flowing, releasing enough water downstream. How can I compute the flow released by a spillway? There is a relationship that comes from fluid mechanics. So let me express the flow through the environmental flow spillway as the product of a flow coefficient μ, which takes a value that is close to 0.385 for a large spillway. Okay, so this is a flow coefficient, and then you have to multiply it by the width of the spillway, and then you have to multiply it by delta H2, and then the square of 2g delta H2 again. This is the relationship that we can use, okay? And from this relationship, we can write it in this way. Let me bring it here. We can write it as μ LC 2g at the power of 0.5 delta H2 at the power of 1.5. And here I can get an explicit representation for delta H2, which is equal to, I can write it here, delta H2 is equal to Q dmv divided by μ LC 2g to the power of 0.5 and everything to the power of 2/3. This is the expression for computing delta H2 depending on QDMV, which we must know, depending on the flow coefficient μ, depending on the width of the environmental flow spillway LC. It is very simple. And it is derived from this fluid mechanics relationship that gives a way to compute the flow through a weir. Now, in a similar way, we can compute delta H1. And now the reasoning is equivalent, but I have to put at the numerator QP, and at the denominator I have to put μ LP. What is P? LP is the width of the diversion spillway, okay, and then I have E to the power of 0.5, everything to the power of 2/3. Okay, so the same reasoning is repeated for delta H1, and of course, by substituting QP instead of QDMV, QP is the design diverted spillway, and using LP, width of the diversion spillway instead of the width of the environmental flow spillway. So this is the way these differences in elevations are computed. This is extremely important because in order for the barrage to work in a reasonable way, you have to make sure that these conditions are satisfied. And keep in mind that this is a simple demonstration, and very often it is the subject of a question at the exam. And my question is, can you please discuss, can you please explain to me how we can compute the difference in elevation between the spillways in a barrage? And what is to be replied is precisely this demonstration. You need to learn by memory, of course, this relationship here, which I am now highlighting in red. You need to start from this, okay? And you need to learn it by memory, or in an equivalent way, this one, and then it's very easy. Any question? Now let me close this, or let me go to the previous one. Let me see. Okay, here we are. Okay, now let's see what happens when the water is diverted. And keep in mind one thing. Sorry, I forgot to say one thing, one important thing. We designed the difference in elevation between the spillways, perfect. But what is the absolute elevation of the spillways? So what is the elevation of the lower one? And the elevation of the lower one is the elevation of the environmental flow spillway. Of course, if you design a barrage with a low elevation, because you put the environmental flow spillway very low, the effect of the barrage is negligible. So this is something that you want to avoid. If you build a barrage, it's because you want to stabilize the water level upstream. So you don't have to put the environmental flow spillway at a too low level. On the other hand, if you raise the level too much, you may create an increase of the flood risk upstream. And in any case, you don't want to exceed the 15 meters, as measured as we discussed before. Because if you exceed the 15 meters, you go under the regulation of the dams, and it's something that you want to avoid, definitely, okay? It's definitely to be avoided. So you have to keep in mind these two extremes, not too low, because you want to make sure that you have some accumulation of water upstream, because in this way you stabilize the water level. Not too high, not more than 15 meters. And then by keeping in mind these two extreme constraints, you design the elevation. Okay, so what happens to the diverted water, as I said? The diverted water goes into this tank. By the way, this is the tank which I showed you in the picture before. In the mountain barrage that I showed to you, there was that tank, you remember? And the tank is, it's called the gravel trap. It has the purpose, as the name suggests, to separate, to remove the gravel from the flow, from the water flow. And the gravel trap may be also integrated with a downstream second trap in order to make a difference between the removal of the coarse grain and the removal of the sand. So if you have a lot of sand, as splitting the trap in two parts may be needed. If you just have gravel, the gravel, one part is sufficient. It's the gravel trap. If you have gravel plus sand, it's much better to separate the trap in two parts, the gravel trap and the sand trap, okay? Here you see that the sand trap is divided into two channels in order to allow selective cleaning. So you can clean the left one and keep the right one operational and vice versa. They are not always divided. This is just an example that you may decide for the sand trap, which requires more frequent cleaning. You may decide to have two channels, okay? These traps are separated by a step. This is a bottom step, okay? Its height is generally around 50 centimeters. Keep in mind that the water level in the gravel trap and the sand trap should not be too high in order to avoid risks. If someone falls into the gravel trap, you don't want people that get drowned, and you want to limit the risk. So the water level is something that usually is less than 1.5 meters, okay? And usually lower than that. In particular for the sand trap, we don't want to exceed the meter of depth, okay? And in this case, the step between the two can be 50 centimeters. And that's fine. And also the downstream end of the sand trap is separated, is closed with a step, okay? We will discuss later what is after this latter step, okay? It's what is called the upstream tank. We will discuss later, okay? Now, gravel trap and sand trap. How can I design them? First of all, keep in mind that for each of them, I need a bottom discharge, and the bottom discharge is located here for the gravel trap and here for the sand trap. And these are called, these bottom discharges, flushing sluiceways. They are opened for cleaning, okay? But you also need a top discharge, because you want to make sure that if you have overflowing from these two traps, the water flows through a way that has been conceived for that purpose and may be protected. And this is the top spillway located here. So you need to design bottom discharges and also a top safety discharge. Okay, very good. Now, how to design the size of this sand trap and gravel trap? What we usually do is to apply a physically based method for designing the size of the sand trap. And the size, I mean the width, this one, and the length, this one. Okay, how can I design them? I use a physically based method, and usually the suggestion is that the gravel trap is pool with the same width and a length that can be lower, up to half of the length of the sand trap. This is an empirical suggestion, okay? In this case, you see that the length is the same order of magnitude, but usually we try to make the gravel trap a little bit shorter in length than the sand trap. What is the reason? The reason is that the gravel is quicker in settling down, quicker sedimentation with respect to sand. So usually the length of the travel along the flow to allow sedimentation of gravel is much lower than the length of the travel to allow sedimentation of sand, okay? Now, how to compute then the size of the sand trap? This is something that we can discuss, and I said that it's we have a physically based method for estimating it. And first of all, let's give an order of magnitude. I said that the depth of the centrap is lower than 1 meter, and the width is a typical order of magnitude for the width is 2.6 meters for each channel. And so what is the way to design the length then? Let's suppose that we have orders of magnitude for the width and the depth. What is the way to design the length? What we have to make sure is that water flowing in the centrap has enough residence time to allow the sedimentation of the sand. Of course, if you keep the water in the centrap for too short time, sand does not settle down. If you give some time, then sand has the time to settle down. And what is governing the time? So how can I estimate this time? So the time is, let me just very quickly open a new sheet. The time needed by a particle of sand to settle down can be computed in this way, dividing h is the depth of the centrap. We can divide it by the velocity of sedimentation. Let me make a sketch. Suppose that you have a centrap here, and here you have the step, the entrance step. This is the step, okay? And here you have some water flowing into it, okay? Very good. Now, let's suppose that you have a particle of sand that is close to the surface and the entrance of the centrap. So what is the trajectory? The trajectory is this one, okay? And the velocity of sedimentation is Ws. Okay, so if I divide this depth h by Ws, I get the time that is required to the particle to reach the bottom of the centrap. And now let me talk about Ws. How to estimate Ws? Let me turn to the red again. How to estimate Ws? I can use the Stokes formula. Now, the Stokes formula, it's can be derived through a physical proof, and the physical proof is presented in my webpage. I don't want to remake the physical proof here because I think you already derived it in other courses. In the past, students told me that this was a repetition. So let me just give you the final result. It's not necessary that you learn it by memory, okay? And it's the final result is what I'm writing here. Now, D is the diameter of the particle. Gamma S, remember this, gamma S is the specific weight of the particle, and gamma is the specific weight of water, and me is it's the water viscosity. So you don't have to remember the formula by memory, but please remember that the Ws velocity of sedimentation depends on the viscosity of water, depends on the specific weight of the particle and water, and depends on the diameter of the particle itself. So you have to fix the diameter of the sand. How to fix it? Usually you have limitations for the water use downstream. So if you have to use the water for civil water supply, you can allow a max diameter of particles in suspension. if you have to use the water for hydropower generation, in the same way, you have a limiting diameter. So the limiting diameter is dictated by the regulations, usually by the water use. So D is given, and gamma S is the usual value of 2,500 kilograms force per cubic meter, and the specific weight of water you need what is, and water viscosity I don't remember by memory, but if you go on any manual, you find it. Okay, so WS, it's easy to estimate, and therefore, this means that you can estimate, again, WS, and then what is the length of the sand trap then? I said that the particle has to have some time, enough time to settle down. So in order to settle down, it takes a time t. So the length of the sand trap is just the product of the velocity of flow times t. T is this one, and v is velocity of flow. What is the velocity of flow? V is given by Qp divided by h divided by the width of the sand trap, and we can indicate it with a symbol like WD. Okay. First, let me say a couple of considerations before I close. And the velocity should be low. Should be low. The lower the velocity, the shorter the sand trap. And the order of magnitude is something like, I would say, 0.05, 0.15 meters per second. This is the order of magnitude of the velocity. And keep in mind that a final consideration, there is an empirical formula which says that LD should be more or less equal to H divided 0.06. So what is an order of magnitude for LD? I have seen sand traps that are like 30 meters long, and let's say that it may range between 10, 15 to 30, 40 meters. And this is the way it's designed. Okay, now let me just go again to the sketch. I think we discussed almost everything but the upstream tank, but I can defer to the next lecture to estimate it. And we will discuss it on Thursday. And then I have some final considerations to make, which again, on Thursday, we will deal with. Okay, students, any question while I am sharing the screen? Let me stop recording.